So we're happy to have Claudiu back for the second talk on computing local Euler obstructions. Take us away.
Thanks. Thank you very much, and thanks everyone for coming back. All right, so last week I gave you a more maybe of a D-module perspective on this and did a simple example of determinant of variety. So today is going to be about another example, but maybe the motivation comes more from intersection theory. So let me start talking about Euler characteristics before Euler obstruction. So there's this famous theorem that says that you can compute Euler characteristics analytically by looking at the zeros of a sufficiently general vector field and counting the zeros appropriately. So in intersection theory, what you would do is you would look at the total Chern class of the tangent bundle restricted to V, and the integral of that would give you a formula for the Euler characteristic, assuming that V is a non-singular complex right? Okay? And one question is, what do you need to do, how to generalize this formula in the case when your variety is singular, okay? And so let me give you some notation. So for my variety V, I'm gonna write C of V for the group of constructible functions. We talked about this last time. And then A of V is just the Chow group. If you wanna use different homology groups, you can, but let me do Chow. And there was a conjecture of the linear Grothendieck that said that there is a natural transformation from constructible functions to Chow homology, which satisfies two properties. First of all, if you look at the indicator function of V and you transform it to a class in Chow and take the integral, then you'll get the Euler characteristic. And this class, when V is non-singular, is exactly the class that you see in this Poincare-Hall formula, the restriction of the tangent bundle, the total Chern class to V. Okay, so I said here natural transformation. So what I mean is that there's a functor here. So you should think of both C and A as functors of associate that give a group, associate a group to every variety. So perhaps we know what the Chow functor does to maps. It's just the usual push forward of cycles. So maybe I should say how C is a functor of map, how it acts on maps between compact varieties. So how do you push forward a constructible function? So if you have a proper map between varieties V and W, and I pick just a subvariety in V that gives me an indicator function, and I want to push it forward to a constructible function on W, well, its value at W is just obtained by taking the inverse image of W, intersect with this Z, and compute Euler characteristics. So in other words, if you think about just mapping V to a point, then the push forward of the indicator function of V is really the same as the Euler characteristic of V. So really, when I talk about this condition, it needs to be satisfied if this star is a natural transformation. It's functorial, right? So I just put it here for emphasis. The question was whether such a natural transformation exists, and that gives this extension of the Poincare-Hall to the singular case. Okay, and so part of the problem is you want to try to generalize this Chern class of the tangent bundle restricted to V. And one possible generalization is this, it's called the Chern matter class. And the way you get that is you look at the Nash blowup for V. So maybe just briefly remind you how that works. You want to embed V inside the non-singular variety X. And then you look at the map from the regular locus to the tangent bundle. You take a point V and you map it to the tangent space. And then you take the closure of the image, and that sort of maps down via the projection to X, maps into birationally to V. So this is a Nash blowup. What's the Nash? Sorry, not the tangent, but you look at the Grassmann bundle. Sorry. So you look at an appropriate Grassmann bundle of dimension V many subspaces of the tangent bundle. So this maps down to so this V tilde is the closure of the image, maps birationally to V. And what this Nash tangent bundle is just a restriction of the tautological bundle on G. You restrict it to V tilde. Okay, and then you do the same operation as we were doing in Poincare Hope. You take the total chair class of this sort of generalized tangent bundle, you restrict to V tilde, and then you push it down to V. And of course, if V was already regular, then you recover the earlier class that computed Euler characteristics. So this Chern matter class would satisfy condition 2 in the Lin-Grothendieck conjecture, but it's not functorial. So what McPherson's realization was that you can modify this in such a way that you do get a functorial construction. And this is with the Chern-Schwarz-McPherson classes. So what you need to do is you take your indicator functor for V, you write it as a linear combination of Euler obstruction functions, and then the CSM class of V would be the corresponding linear combination of Chern classes of these subvariety, Chern matter classes of these subvariety. And McPherson's theorem was really that this definition gives you the right functoriality, and it generalizes the notion of the total Chern class of the tangent bundle. Okay, so these Euler obstruction functions were used to prove the Lin-Grothendieck conjecture. Okay, so this is how Euler obstructions show up in interception theory, and again, basic set of questions: how do you compute these classes, right? So you want to find algorithms to compute these Chern classes, and then it turns out that they often satisfy some positivity property in the effective classes in the child group, and you want to, when that happens, you want to be able to establish these properties. And one of the first examples you might want to look at is you look at the generalized flat variety, maybe a Grassmannian, and you look at its stratification by Schubert cells. You take the closure, these are the Schubert varieties. The Chow group is just the free group on the classes of these Schubert varieties. What you would like is, you take one of these CSM or Chern matter classes, you express it as a linear combination of with respect to this natural basis, and then you want to understand the coefficients and whether they're positive or not, right? And so, for instance, some results in this direction is Alufi and Mihalcha. They provide some algorithms to compute CSM classes of the Schubert cells, and then their conjecture their positivity. This was known in the case of the classical Grassmannian by some earlier work of Hu, and then again recently with Alufi, Mihalcha, Schurman, and Su proved that again for the Schubert cell, these coefficients are non-negative in the case where you look at CSM classes. And then more recent work of Mihalcha and Singh was to try to understand the Chern matter classes. And again, you could look at this in the general situation of arbitrary generalized flag manifolds, but I don't think many results are known in that case. And so these guys just restricted to the case of co-minuscule spaces. So I'll talk about some examples, but this is basically the usual Grassmannian, orthogonal Grassmannian, Lagrangian Grassmannian. That's a finite list of quadrics in projective space and some two more exceptional examples. So again, it's maybe the first generalization of the classical Grassmannian is this class of co-minuscule spaces, and you might want to try to understand how to compute these classes. And they had some algorithms to compute Chern matter classes and to prove, and were able to check positivity in some special cases. And really, what it boils down to is to prove that the local Euler obstructions, this matrix E that I talked about last week, the local Euler obstructions associated with this Schubert stratification are all non-negative numbers. Okay, so from this list of co-minuscule spaces, one of the ones that was left out was the case of the Lagrangian Grassmannian. So I want to focus on that today and try to explain how you describe Euler obstructions in that case, and how you can establish their positivity. Okay, this was more of a motivation, and I want to talk about a specific example for the rest of the talk. Okay, so I take n to be a positive integer. I look at this symplectic vector space, so dimension 2n with a non-degenerate skew-symmetric form. There is a natural flag in C2 to the 2n. Just take the standard basis and look at the subspaces, order it from 1 to 2n, and look at the subspaces it determines. And you could define, you could look at the Lagrangian subspaces in C to the 2n. So this would be n-dimensional subspaces where the restriction of this form omega is trivial. And then you could classify the Lagrangian subspaces according to how they intersect the standard flag in C to the 2n. And it turns out that the natural parameter set is the set of partitions with at most n parts, each of which is equal to at most n. So they fit in, their Young diagram fits inside an n by n rectangle. And moreover, it's symmetric, it's equal to its transpose. Okay, so this is a well-known Schubert stratification for the Lagrangian Grassmannian. And there's, of course, the Bruchau order, which is defined in terms of the stratification, whether a stratum is contained in the closure of another. But if this happens, we declare that lambda is smaller than or equal to u. Okay, and so again, the the indexing set is this set of symmetric partitions. And it turns out that there's a more convenient parametrization in terms of just words in an alphabet with 2 letters. So let me explain this, and because the combinatorics will be relevant in understanding the behavior of the Euler obstruction. Okay, so how do you get from a partition to a word? So I'm gonna shift my partition so that the corner is just on the bottom, and so that we can see the symmetries over here. So we draw a partition by a Young diagram, maybe rotated by 45 degrees. So these numbers are simply the number of boxes in each row, if you want, a column of the partition. So I have this axis of symmetry, and of course, if I know what happens to the left, then I can determine the whole partition. Okay, and so this symmetric partition is simply determined by a path. So I basically forget all the boxes and only record this path over here. And then the directions in this path can only be southwest to northeast or northwest to southeast. So whenever I go up along the path, then I'm just going to write the beta. And then whenever I go down southeast, I'm just going to write now. Okay, so I guess if I describe it in this way, then it's clear that the number of cells has to be a power of 2. So namely 2 to the n. Okay. So this is the indexing set for my Schubert cells. I'm going to write the size of the word W to be just a number of letters, and also use this notation to count the number of alphas. And a similar one for beta. So, okay, so that's the basic combinatorics that describes the cells in the Lagrangian Grassmann. And if you want to know what it means in terms of Lagrangian subspaces, you have to go back and decipher the definition in terms of the partition lambda and the intersection with the standard flag. All right, so this conjecture of Mihalchand's thing about the positivity of Chern matter classes really boils down to computing the local Euler obstruction. So again, VW is a closure of a stratum, is a Schubert variety. I evaluate at a point in a Schubert cell. I get a matrix of size 2 to the n by 2 to the n of local Euler obstruction coefficients. And what they're really saying is that these coefficients are non-negative for every y in double. And so they make this conjecture for communiscal spaces. For instance, they verified in the case of the usual Grassmannian and the orthogonal Grassmannian. So maybe I'll make a comment about why these cases are a little easier later. So, and of course, once you prove the non-negative stability statement like this, then you might ask yourself, so what's the border case? When do you get the vanishing of this number? Okay, so that was the goal of our work, to basically understand this Euler obstruction for the Lagrangian Grassmannian and then prove this positivity. Okay. And as I said earlier, there's two things you might want to ask about. One of them is algorithms to compute these numbers and then establish some properties like positivity. So in fact, there's old work of Bo and Fu who give a recipe to compute these numbers, but that somehow involves both positive and negative contributions. So what we do is basically we sort it out in such a way that really we realize these local Euler obstructions as the solutions of a counting problem. So it's a manifestly non-negative number. And since it's a solution of a counting problem, it's also easier to sort of detect when the borderline case happens. And so what is the inspiration between realizing these Euler obstructions as as solutions to counting numbers? So it comes from classical work on Kasdan-Lustig polynomials and realizations, combinatorial realizations of this Kasdan-Lustig polynomial. So the point is that, at least in this case of of sugar varieties, there is the behavior of local Euler obstructions it is in some sense similar to that of Kasdan-Lustig polynomials. At least they have a similar flavor. So what these Kasdan-Lustig polynomials determine is the intersection homology of groups of local intersection homology groups of IC sheaves. And so in particular, if you look at some just plugging -1 in a Kasdan-Lustig polynomial, you're going to get the local Euler characteristics of IC sheaves. And so if you believe that Euler obstructions are closely related to this local intersection homology Euler characteristics, and in fact, they're the same in the situation where characteristic cycles are irreducible, that's what we were talking about last time, then you should think that there is a parallel between these two. Okay, so in fact, the Euler obstructions can be computed on the nose from Kasdan-Lustig polynomials, maybe evaluated. Let me say -1 in the case when characteristic cycles or singular supports are irreducible. And the point is that happens for the usual Grassmannian, for instance. It happens for the orthogonal Grassmannian. So whenever you have irreducible characteristic cycles, you compute Euler obstructions directly from Kasdan-Lustig theory, and then we know enough to establish positivity. So somehow this is why these other cases were slightly easier. In the case of the Lagrangian Grassmannian, we know that the reducibility fails. And so all I'm saying is that the Euler obstruction and the Kasdan-Lustig polynomials have similar behavior, but there is always an error term. There's always a distinction that's measured by this characteristic cycles that get more complicated, okay? So all I wanted to say is that I'm going to look for a description of Euler obstructions that's somehow analogous to that of Kasdan-Lustig polynomials. And so then it's natural to think that there should be some combinatorics that matches the combinatorial description of Kasdan-Lustig polynomials. And there's a lot of work in the 80s on Kasdan-Lustig polynomials. So it starts with Lascaux and Schulte-Berger in the case of the classical Grassmannian, and Bow has done more work on other communistic spaces. And I will explain some of the combinatorics, but the idea is that to every word parameterizing the Schubert cell, you associate a tree. If you're interested in, if you look at the pair of words, right, as you should when you compute this Euler characteristics, then on top of the tree describing associated with W, you have to add some decorations. And then you define labelings associated to this diagram, and then the theorem will be that the number of labelings of this diagram is the Euler, the local Euler obstruction. And again, you should think of this analog as an analog of the description of Kasdan-Lustig polynomials in terms of labelings of rooted trees. Okay, and so I don't think there should be any surprise that these two that we're seeing the same combinatorics for Euler obstruction. Okay, so maybe we could start from scratch now and explain just some of the classical combinatorics that comes into this Kasdan-Lustig or Euler obstruction. Okay, so this is going to be basically for now independent of what I was talking about earlier. So I should fix an alphabet with 2 letters, and then I'm going to consider a subset of the words, which is special. It is obtained recursively as follows. So it contains the empty word. Whenever you have an ordinal alphabet and then you add an alpha at the beginning and a beta at the end, then you get a new word in your dictionary. And then this Z should be a monoid, so it should be closed under concatenate. So for example, I start with the empty word, maybe I add an alpha beta, I concatenate with itself, and then maybe I stick it in between an alpha and beta, and maybe I concatenate with another alpha beta and so on, okay? And so you may be more familiar with this monoid Z in terms of parenthesizing expressions. So this is sometimes called the monoid of parentheses. So such a word in Z corresponds exactly to a valid way of parenthesizing an expression of a certain length, yes? So this is the basic combinatorial object. Again, it gives you some special words in this alphabet. And what Lascaux and Schützenberger do is they think of such a word as a rooted tree. And the way you construct the tree is, well, for the empty word, the tree is just one vertex. Whenever I introduce a pair alpha beta, that corresponds to a new edge in the tree. And so whenever I have consecutive alpha betas, for instance, then what I'm doing is I'm joining the corresponding edges to a vertex. So this would be this guy. And now when I attach an alpha beta around the existing subword, all I'm doing is I'm attaching an edge up here. And then I guess I have to concatenate with this extra guy. And that's this extra, okay? So anyways, there is a combinatorial method to attach to every word in this monoid Z a tree. And in fact, these two pieces of information are completely equivalent, because if you have the tree, then you can go back and read the word. And so actually, let me do an example, and then I'll show you how to read the word from the tree. So I have this expression Z. To get to the tree, I have to parenthesize it. All right, and so this red parentheses again correspond to these two edges, and I need to add on top of it the green one, and then concatenate with the blue edge. And so this is how, again, how you get from the word to the tree. If you want to get back from the tree to the word, all you need to do is you start at the root, and then you travel the tree along the boundary. And whenever you move down, you write an alpha, and whenever you move up, you write a beta. Okay, so that's about the basic structure of this submonoid. It corresponds to rooted trees. Okay, so of course, not all the words in alpha and beta are of this form. So let's extend the monoid just a little further. I'm going to write Z tilde. This is obtained from Z and possibly a bunch of betas, right? So then I have words in the monoid of parentheses, and they're intertwined with a bunch of betas. Again, this is not everything, but it's just yet another approximation of the dictionary words in alpha and beta, okay? So to such an expression Z tilde, I'm going to again associate a rooted tree as in the last Cauchy and Berger work. All I'm going to do is just ignore the beta. Okay, so for instance, in this example, I do the parentheses in all possible ways, and then I'm left with a bunch of betas that I need to ignore. And so I draw the tree, and it's the exact same tree from before. So of course, it's no longer the case that I can recover the word Z tilde from the tree, because I'm dropping that. Okay, so it's just a one-way street for now. And in general now, if I have an arbitrary word W in the alphabet alpha with two letters alpha and beta, then you can express it uniquely as a concatenation of words in the monoid of parentheses intertwined with this alphas, and then the leftmost subword may have to be in Z tilde. You may end up with some extra betas that are not that you're not able to match. Okay, so every word has such a unique decomposition, and what I want to do is just attach a combinatorial diagram, some generalization of these rooted trees to this W, and again, I want to then use the combinatorics of the tree in order to describe the Euler obstructions as a solution to a counting problem. Okay, so what's the combinatorial diagram that you attach to a completely general word W? Well, you will have, first of all, you will have some distinguished nodes. So each of these nodes corresponds to one of the subwords in Z for the extended monoid of parentheses. Then there will be distinguished edges joining these vertices. So there's going to be one distinguished edge for each of the alphas. Right, so these days R of these alphas correspond to the letters alpha in the expression for W. And then to every VI, to every distinguished node VI, I'm going to attach one of these last Cauchy and the Jeffries. Okay. So, and then edges in that subtree are going to be regular edges as opposed to these distinguished edges. That's what they're moving from one plus Cauchy and the Jeffries to another. So I know this is maybe a little much, so it's probably good to do an example. Again, it's just about how well we can parenthesize things. So I have this alpha beta and alpha beta and another alpha beta, okay, and another one. So I can also pair these two guys, and I think that's it. So so what are my ZIs? Well, there's a Z0, which is empty. There is this Cauchy and J word Z1, which corresponds to this subtree. There is also a Z2 here, which is again empty. And then there is the final guy here, which is a Z3, which again, it's a last Cauchy and J word extended by the beta. So really the tree is just one line. Okay, so there's a very explicit way of constructing this tree with distinguished and regular edges. So these distinguished edges correspond to the three alphas already. Okay, so again, you have a cell in the Lagrangian-Grassmannian that corresponds to a word W in the alphabet alpha and beta, with letters alpha and beta, and to that I will attach this combinatorial get. Okay. Oops. Not sure what happened here. So now I need to talk about Euler obstructions. Those depend on pairs. So what I need is I need an additional information on top of this diagram that keeps track, on top of the diagram of W, that keeps track of the word Y. Okay, so and the additional information would only consist of various decorations of the terminal edges of AW. And so basically I'm adding certain capacities for these terminal edges, which have to do with how the path Y sits relative to the path of W. Okay, so, and this is the same example as before, W. So that's the shape of the diagram, and I'm going to explain to you how you get these numbers, capacities, right? So this is best explained by drawing the diagram of W and then the diagram of Y. The condition that Y is smaller than or equal to W in the Bruja order is simply the fact that Y lies below W. If this fails, then one of the basic properties of Euler obstruction says that it has, the corresponding Euler obstruction has to be zero, just because this cell lies outside the Schubert variety of W. So we should only focus on situations where the path of W lies above that of Y. And then you can identify this terminal edges in your tree as troughs in the path of W. This is, subwords of the form alpha beta, or it means just it's valleys inside this mountain range. And I guess the last terminal edge is basically this. The last letter is an alpha, then you think of that also as a value. Okay, and then you basically measure the lattice distance between the path of W and the path of Y, and that explains this later. Okay, so it turns out that this diagram over here is all you need to know about Y and W, because there's certainly really a lot of information when you pass from the pair to this diagram, but it's all you need to know to understand the Euler obstructions. Okay, so I guess the final ingredient is the notion of a labeling of the diagram associated to W and Y. So first of all, there's a natural ordering on the edges of the tree. When you're saying that F is smaller than F prime if it's closer to the root. This is the root. And another way to say is F is above F prime in the diagram. Okay. So what's an admissible labeling? Well, it's admissible. It's a labeling of the edges. So I have to attach to each edge a non-negative integer. These integers have to respect the ordering of the this partial ordering on the edges. So if I'm closer to the root, then I have to have a smaller label. If I'm on a terminal edge, this is where the capacities come into play. They give you a bound on the label of the corresponding edge. In the case where this E1 is a terminal edge, like we had before, meaning there's no subtree attached here, then the label of E1 should be exactly equal to its capacity. And then there's some formula here that tells you that basically the odd distinguished, the label on an odd distinguished edge is essentially completely determined by what happens below that edge. And finally, this, just if you restrict to distinguished edges, these labels have to respect parity. They come in pairs, having the same residue class modulus. So again, it's, there's a lot of rules here, but each of them is something that's easy to follow. So I gave here an example of an admissible versus a non-admissible labeling. Well, for instance, this is admissible because the label of this distinguished edge E1, which is also terminal, is equal to 4. These two are different, so that violates one of the conditions in the definition of admissible labeling. Here, as you go up towards the root, the labels decrease. Well, whereas here, they do not. We go from a label of 1 to 2, so that's another problem. There is perhaps, then I said that these labels should come in pairs that are congruent mod 2. So these two are congruent mod 2. These two are congruent mod 2. So that's okay. There's some, maybe there's some subtlety in the definition which I didn't quite explain. You should imagine that this continues on with labels 0. And if you imagine that this continues on with label 0, then we have a problem here because these are distinct mod 2. So anyways, there's many problems with this diagram. There's many reasons why it's not admissible. And you can have fun looking at these notes later and check that the diagram on the left is indeed admissible. Okay. So again, the theorem says you start with a pair YW, you associate this diagram. Each of these admissible labelings is supposed to contribute 1 to the local Euler obstruction. So again, I have 2 examples, but again, in the interest of time, I'll let you have fun with this. And maybe just explain why the diagram on the right cannot possibly have any admissible labels. So this corresponds to a pair Y smaller than or equal to W. So that means that the cell is contained in the closure. So there's no a priori reason why this vanishing has to hold. But what I'm telling you is that this is a situation where the vanishing does. And so let's think about how this would work. So if you have an admissible labeling over here, then this number should be equal to 3. Every number in here should be smaller than or equal to 2 because of these capacities, and should be congruent to 3 mod 2. So this label is necessarily equal to 1. And then one of the conditions was that if I look at, an edge like this, every odd edge is determined, the label on an odd edge is determined as the minimum labels of all the smaller edges. So this is a minimum of labels on smaller edges. So this guy has to take the value 1. And because of this other imaginary label of 0, these two have different parities. So it's really, this shows that it's impossible to find any admissible labeling for this pair YW. Okay. And so once we understand that these local Euler obstructions are count number of admissible labelings, then the question is to understand when they're 0, so this limiting case, which is to understand when a diagram like this has no admissible labelings. And I've drawn, maybe ignore the theorem for a while, I've drawn here an example of two paths y and w, where y is between w. So what can happen is that, it can happen that y is strictly below w. So every point on y is strictly below a point in w, or they can meet sometimes, like in this example. Yes. And now if the paths meet, then you can just look at the last time they meet. Just completely ignore everything that comes before this point. And the question of whether the Euler obstruction is 0 for the pair y and w is the same as whether y double prime w double prime is not 0. So in fact, these two differ by a scalar multiple. And so, so if you want to characterize the vanishing, then it's enough to assume that you look at pairs of paths where one is strictly below the other. Okay. And so if that happens, then again, there is a very simple rule for explaining when the Euler obstruction vanishes. And it's just, you have to just take the difference between the number of alphas in the two words. You have to count the number of distinguished edges, or another way to say the number of alphas in this decomposition of W. And then you want to make sure that the Las-Cauchy and Berger trees is attached to the even words Z, they're in fact empty. Again, it's some very they're easy to check combinatorial criteria. And so, for instance, in this example, just going to focus on one of them. In this example, this number is really the same as the capacity of the last. This capacity, which is the capacity of E1, really, and this is even, so that's what makes the Euler obstruction non-zero. And if you check the example we had in the previous slide, this one actually satisfies all the conditions, and that's why UIW is zero. So this capacity is an odd number. There's an odd number of distinguished edges, namely 3. And then the even subtrees, well, this is a subtree, an even subtree, and this one, they're both empty. Okay, so maybe, so what I'm telling you is that there's this, there's an easy to check combinatorics that determines this Euler obstruction. And maybe just make one more comment. Is that if you, for casualistic polynomials, you have a similar combinatorial scheme, but what you could do is you can weight each labeling by a monomial, so Q to the sum of the labels. And that's in fact, that's the way you encode casualistic polynomials combinatorial. You don't just get numbers by counting labelings, but you have to weight them appropriately by this Q. And I guess computing the Euler characteristic then corresponds to plugging in the value for Q. So of course you can just do the same. You can also weigh the admissible labelings. And then what that gives you, it gives you some polynomial with value at 1 or minus 1, at 1 really, is the local Euler obstruction. And so for Kazan-Lustig polynomials, there's an obvious interpretation of the fact that its value at -1, it's really you break it up into contributions coming from the individual homology groups. But for these local Euler obstructions, I really know no interpretation of these polynomials. So I mean, you can construct them, I guess, but I'm not sure if there is any good way of breaking that, and whether this local Euler obstruction number comes maybe as a contribution from more subtle invariants. Okay, so maybe I will stop here. Thank you.
One too. Great. Yeah, thanks a bunch for an interesting talk. Does anyone have any questions for Claudiu? Oh, maybe I'll start with something. So yeah, so now I'm curious about just in a vague and general way about these Lagrangian Grassmannians. If people studied them from a commutative algebra perspective, in terms of, the usual stuff, singularities and things like that.
Certainly, yes.
Okay.
I'm not, but I mean, I am not sure what.
It's a vague question.
Whether that counts as a commutative algebra, but maybe one comment to make is that if you have this Schubert stratification, which you could do with respect to a Borel group. There's a choice of an opposite Borel, and if you look at the maximal cell in the opposite Borel and you intersect it with the Schubert stratification, for instance, one thing you would get is you would get the symmetric matrices and some kind of matrix Schubert varieties for symmetric matrix. So some interesting stratification of the space of symmetric matrices. Which refines just the stratification by rank.
Okay.
So I guess certainly I'm sure people have done a lot of commutative algebra with that.
Yeah.
I guess that's one way of putting it in an affine setting then.
Okay.
And then you could do a lot of commutative algebra in the affine.
Yeah. Where would you recommend somebody, just read a little bit more about these?
I think maybe there's Lakshmi Bai has a book called Flag Varieties.
Okay.
Maybe actually they have several. There is a book, maybe Flag Varieties and Interplay of Geometry, Combinatorics, and Representation Theory. But I think there are many. I think if you look up Lakshmi Bai, maybe you'll find several. Yeah, so there's one that's called Singular Loci of Schubert Varieties. And that answers your previous question.
Okay. Yeah, thanks.
Yeah, there's this standard monomial theory approach to studying the Schubert varieties. So then that's some commutative algebra.
Okay.
But maybe for the combinatorics of these combinatorics of trees, then you would go to the Raicu and Schutzenberger paper. It's in French. It's Kazan-Lustig polynomials.
Okay.
So the Grassmannian, and then Bo has done some more work giving them that for this other communist papers. I think this combinatorics is really about, it's not about, it's about the causalistic theory.
Thank you.